so next up for the Mark II is gonna be kind of a deep focus into the right arm. That's what I've been working on mostly recently, and there's a lot of subsystems that go into it. There's like the blades, you know, the rockets, all that kind of stuff. My idea is that I'm basically gonna hone in to each subsystem. Each one's gonna get 2 videos. So there's gonna be a deep dive, kind of more of a technical science engineering kind of style explanation of each system. And then there's gonna be the cool stuff, you know, the videos, the testing, all that fun stuff in a separate video. So if you're more like, oh, I like the science, I like the engineering, I like that kind of stuff, then that's for you. But if you're more like, man, I just wanna see all the cool stuff, the fire, you know, I wanna see like a watermelon get stabbed. It's like, we can do that, you know, and that'll be its own thing. But other than that, it's gonna be kind of split up. And today's video is gonna be more of a technical deep dive into the side blades. So the idea with the side blades is kind of like combining a Batman style accessory with my Iron Man suit, you know, kind of mixing 2 different things together. You have like your Batman-esque kind of vigilante thing, but you're combining it with more like your hard tech Iron Man suit. But the idea is that it's gonna be kind of a cool fusion. You know, you can think like one of those restaurants that's like Mexican and like Thai food, but it's like Batman Iron Man. You want to think about how his thing works. You know, it's kind of like a gauntlet that he wears in the Dark Knight. The blades pop out. They also do shootout. We're not going to do that. That's a little much. Plus, it's like we're doing some other thing. But since that's fake and this is real life, you kind of have to think about how that would work in a practical sense, in a low profile way that would fit nicely into the suit. You know, we don't want anything to be clunky. We don't want it to take away from other subsystems that are also cool. And here you can see them in action, right? They're moving up and down when I send the commands through my phone. And that's running through a larger kind of wireless ecosystem that I wrote for the suit so that it can communicate through like a Wi-Fi network versus like a bunch of wires. And I can talk about that, you know, later. But essentially they move up and down, and they stop at their up and down positions based on the phone commands. And that's kind of the you know, the gist of everything. That's what we're trying to get. You know, we're not trying to get anything fancy for these guys at least. We just want them to move up and down and kind of keep their position strongly when I tell them to. So kind of the first idea I got for that was this thing here. So you can see there's these guides that move this piece up and down as it's rotated from the back. You can kind of see that there. It works in principle. The motion profile's there. It moves up and down as you move it, but it's not aligned well. You need really tight tolerances for it to actually work the way I want it to. So in principle, you know, in CAD, it always works, but in real life, it doesn't. Also, that mechanism was designed to work with a servo motor. And you know, that's a pretty common thing to use in like a hobbyist setting. You get an integrated motor driver, you got an integrated sensing system, and you get a couple gears in there. But the actual motor itself is gonna be too small for what we need to do. So the actual force output, granted we're getting all these benefits, is not as nice as we want it to be. So that's kind of where I ended up switching to a stronger DC motor with a gearbox built into it. So with this new motor in mind, and also wanting to keep the original motion profile from that mechanism, the idea kind of ends up settling at a 4-bar mechanism, which is a pretty straightforward parallelogram style system where you just have 2 beams like this, and they're coupled at the top by a linkage, which would be the blades. And then the motor rotates 1 linkage and the whole thing kind of moves up and down. That works out pretty good for getting the blades to move how we want them to, but then we have to worry about the strength of the mechanism because now the motor's locking itself. So now all the load is being transferred to the mechanism itself and the rotational joints, which I'll get to in a second. But that means that these 3D printed linkages that I'm using right now, they need to be beefed up, otherwise they're gonna break, you know, or bad things are gonna happen, which we don't want. Also, the micro bearings that I was using in these 3D printed linkages, they're very small and their inner diameter is tiny, so the shaft that goes through them is also very tiny, and all the shear stress from like impacts and things like that are going straight to the shaft as well, and then they're gonna break. So the shafts are too small, the bearings are too small, the linkages are too weak, so we have to beef those guys up. They're not really getting the job done like we want them to. And you're probably wondering about the sensing mechanism. Like that's something that's pretty important for this system. You know, I initially tried an encoder, which as a sensor works great. I mean, that's what like most state-of-the-art things use, but it just wasn't doing it for me. You know, what's kind of a better, more elegant, more classy way, kind of low profile, sleek way to get my measurements for this system? I want to be able to tell me when it's at the top and when it's at the bottom, but I don't really care about what's going on in between. I mean, that's not important to me. That's like, it's whatever, right? You can think limit switches, they're in 3D printers, you know, they tell you when the motor's at its end position, and that's it. You don't have to worry about anything else. But they're too big for what I'm trying to do. I can make my own custom switch, I can make some sort of electrical contact, but no. We're gonna go with something more classy, you know, a little bit more mature, more elegant, something that kind of speaks to me just a little bit more, you know, there's better vibes between us. And I was thinking more like a Hall effect sensor. So that works great because it kind of detects magnetic fields as they get closer. And there's a certain point where the signal just maxes out because the magnet is just too close. So with that in mind, I'm like, you know, I can almost use it as a discrete position tracker where I have a certain magnetic field threshold at each position by placing a magnet under the path of motion. As the linkage moves, I'm not really sensing any magnetic field because they're going to be away from the linkage during the motion. Going from the encoder to the Hall effect sensor, I had to switch up my design a bit. I can't have it coupled to the shaft anymore. I kind of lose that ability. So what I did is I turned one of the linkages themselves into the sensor. So the Hall effect sensor being implemented into the linkage required a bit of an assembly process. I had to, custom design this metal linkage, which isn't too crazy, but the sensor itself also had to be custom designed. Otherwise, I'd have to be buying like an off-the-shelf breakout board and dealing with those dimensions, and that's just not the best. So I made this micro kind of adapter board for the Hall effect sensor that just assembles with the linkage. It works in principle. It gives me the sensing ability that I want. I can actually capture the magnetic field up and down, but since I'm using a circuit, I have to have an electrical connection that gives me the power and the signal to the sensor, while also being able to go back to the microcontroller and to give it the information of what it's seeing. So with that whole electrical connection in mind, you can imagine that just having wires coming out of the sensor that's moving up and down are going to be prone to fatiguing, they're going to bend a lot, they're going to break. And that is one thing that ended up happening a lot. Like, I had to deal with breaking. I only got a couple tries before the wires actually snapped off, and it's like, it's a whole thing, you have to resolder them. Obviously, it's not going to be a robust thing that can last long, so I had to kind of already start rethinking the sensor itself. I was going to stick with the Hall effect sensor because I liked how low profile, I liked how well it fit into the whole kind of the sleek design of the side blades. It kind of fit in well with that, right? So I didn't want to lose it, I didn't want to get rid of it, I didn't want to switch to a different sensor, but it was already giving me problems with the electrical connection, so we kind of had to refine that a bit, get a little bit better in that regard. And as those refinements kind of came along, I also started increasing the strength of the linkages. They were, like I said, originally 3D printed, but they ended up becoming metal because they're just a lot stronger that way. And there was also another problem I was having in the background during the sensor redesign, and it was that the 4-bar linkage that we kind of settled on originally, this kind of parallel motion, wasn't getting it done for me. It would move in principle, it would move every once in a while the right way, but because I was only using 2 linkages, sometimes it would go out of alignment and one would be up and one would be down, and it would just be completely stuck that way. And that's also not great for a robust mechanism, because if I'm also impacting anything, the chance of it going out of alignment during an impact is pretty high. So we had to kind of reconsider that. We can't really stick to the nice 2 linkage system that we had originally. So I added a 3rd one in the middle, and that seemed to help a lot. You'll also notice the motor moved from the side to the middle as well. It gives me actuation from the center, which is a lot more stable in terms of doing it from either end of the mechanism. And you might be thinking, oh, that's great, the mechanism works now. And it does, but we're still having that sensing problem. And that's something that we're gonna have to overcome if we want it to be actually usable. At a certain point, I have to put this thing on, and it has to work repeatedly during tests and stuff. So thinking primarily about the electrical connection to the sensor, that's one thing that I need to have during the motion, but I don't need to necessarily do it with wire. You can think charging pads, right? That's one way to apply power, but then we also have to receive a signal somehow to get my sensing data to the microcontroller. And that isn't done as easily with an inductive coil. So we can't really do wireless communication for the sensor unless the sensor becomes itself its own battery powered microcontroller, which is potentially a thing, but for the size that I'm working with, it's just not possible. So it still has to be some solid electrical connection that can persist during the motion, but also not give me failure points where there's wires, right? So the idea I started thinking about was slip rings. They're these mechanisms that allow you to rotate multiple times while also maintaining an electrical connection as you do that. So the way those work, they have these brushes that are constantly keeping contact. They have a little bit of a springy ability that maintains contact with a conductive piece as it rotates. In my case, I didn't necessarily need continuous rotation. It's really only a couple of degrees of motion that this linkage is moving. So that idea kind of made its way to the sensor, and I ended up using these things called pogo pins. A lot of modern just electronics have them nowadays. They essentially just are little springy electrical pins that you can solder onto stuff. And I made a sensor kind of designed around using those as connection pieces. But I took it one step further, and instead of using the linkage as an assembly point for the sensor, I just turned the entire linkage into the sensor itself. So the company I use to make PCBs also makes aluminum PCBs, which essentially give me the strength of my metal linkages that I wanted, while also giving me the sensor built in, so I don't have to worry about tapping these tiny holes for small screws and all that. I lose all that, right? So now I just have one thing, it's my linkage, it's my sensor, and now I have the pogo pins onto it as well. So now I get a constant electrical connection through the motion while also getting a nice robust linkage. Boom. So that's one half of the electrical connection side. So there's the actual linkage and the pogo pins, but then you have to think about the mating side. What's on the actual frame of the suit itself that's sending and receiving those electrical connections from the linkage. So what I ended up using was these tiny little copper tracks that I designed that just press fit into the frame, and the pogo pins maintain contact with them during the motion, and that works well. Like, you know, I get what I want from them, but they're just not easy to design around since they're so tiny. So I ended up turning those three into an actual PCB itself. It just has exposed traces on them, and then I get one piece that gives me the 3 connections, and then I can, you know, save a lot of design space and don't have to worry about such tiny features in the design. And hey, that's where we are now. It's like a nice, stable kind of fusion of a stronger mechanism, a better sensor, and better actuation. And we kind of get the, you know, that motion that we saw at the beginning. Now the next step is finding out how to make it wearable. Right now, everything is very messy. The wires are kind of everywhere. It's not clean. If I put that thing on, the chance of the wires getting snagged during motion would probably be pretty high. So taking steps towards that direction, I already have these custom microcontrollers and custom motor drivers that I've been designing. And they get the job done, but also I'm still using wires to connect everything, and that is still a pain. That's why it looks like a rat's nest in that video at the beginning. The custom drivers and the custom controllers are part of the larger electrical ecosystem of the suit that give it a little bit more refinement. You know, using like an Arduino or like a breakout board for these drivers, like off-the-shelf components, works out good enough to get me to like testing everything. But in terms of wearability, I need everything to be within a suit. So these are kind of being embedded into the actual structure of the suit so that the electronics and all the wiring kind of flows nicely with the actual suit design. Otherwise, I need to have all these external wires, and I mean, honestly, this is gonna end up being a whole other thing at some point, the electrical kind of nervous system of the suit, if you will. But for now, we're kind of in a nice spot with it. So that kind of wraps up this technical deep dive into the side blades. Let me know if you wanted me to go even more in depth. I don't know the kind of maturity level in terms of the engineering behind this stuff that you guys are familiar with. So if you want more, if you want less, let me know. This is kind of the beginning of a lot more videos that I'm planning on posting soon. Hopefully we can kind of get those rolling faster. We'll see, you know. Main blades coming next, then the flamethrower, then the rockets, then the side darts, and then all the test videos that come with that as well. So they're all gonna be a fun little series putting together. I think you guys will like it, hopefully. You know, we'll see.